Alrighty, I go with circuit changes 5, and I make all these different changes to this circuit. Then I go to circuit changes number 6, and I make other improvements to these circuits. And now circuit changes number 7, and I add more circuitry and take notes and experiment and keep on doing these things. So I have all this elaborate circuitry going on here, trying to find that best torque converter I can make for this kind of application. And I'm just working with it and working with it, and every one of these circuits work proper. They work really well. And I build them and I breadboard them, and they work really proper. But there's only one thing that I didn't consider, and that was a change in the supply voltage. If I want to adjust the motor speed, I want to adjust the voltage to the motor. And every one of these will work within a certain range of voltage change, which would be motor speed change. But they don't work to have a variable speed on the motor. And so after thinking and thinking through this, after going through all this circuitry, I began to think there's got to be a better way to get this down to a science where I can have it work perfectly with the fewest amount of components necessary, and to make it work just so accurately with no bugs to work out anymore. And here it is. Very, very simple circuit. This is my torque converter circuit, my version of one, that will put a voltage across the motor, and when the motor begins to have a load put on it, the voltage will immediately go higher across the motor to keep the motor current coming stronger and stronger. As long as when the motor goes to complete stall, this drive transistor here that drives the motor will be close to saturation, whatever it takes, but it will be at full value. And this works really well. It works for my toy motor right now I'm using for experimenting. I can go from 3 volts up to 6 volts across the motor, and it works proper with torque. I'll give a demonstration here how this works. Right now I have 3.5 volts across the motor. That is the direct reading across the motor. I have the setup right here. This red light right here, this LED here, is an indicator. That's an indicator that there is feedback current from the motor continuously coming back. And that's what this is right here. That's the indicator. Whenever I install the motor, this way here, that light will come on stronger. And then the voltage across the motor goes up. A small little load here. Watch, I'm going to put a small load to the motor. Just every little bit I put on there will cause it to get better, stronger. And when that lights up more and more, the voltage goes up. So now, right now, there's no load in the motor. Now there's a load in the motor. Now I'm going to stall it completely. The motor is now completely stalked. Under full stall, as you can see what's going on, under full stall, the light is at maximum and the voltage across the motor stays. As long as that light is on, it's going to continue to feed current to the motor. Here's how it works. Okay, so now this is no different than the other ones I've made where the voltage went across the motor higher as the stall came onto it. But here's the difference in this circuit here compared to the other circuits. I'm now going to increase the voltage across the motor with the power supply. As I increase the motor, I'm going to increase to 4 volts now. I'll go 4.5. I'll increase by 1 volt now from 3.5 to 4.5 volts. Again, I got my feedback on here. I'll go ahead and stall this. The light comes on stronger. It starts at 4.5 and increases to about 5, 5.3. Again, we got the feedback. Now I'm going to increase the voltage across the motor to 5.5 volts. Okay, 5.5 volts. Got feedback here. Now I also have the ability to adjust this feedback to make it less sensitive here by adjusting this here variable resistor here. Okay, so now I'm at increase to 5.5 volts here now. Around there. Now the light's not on yet because I don't have any load in the motor, but now I go ahead and touch the motor here and the light comes on. So I'll touch the motor, the light comes on. The voltage goes up. Now it's completely stalled. Now if I go too much, too high voltage, I have to adjust the resistors here because now I have current flowing out the base, and then it will draw current away from the opto-isolator. But under normal running conditions with a load on there, I got plenty of torque, got nice feedback. I have the ability, as I said, to be able to adjust the voltage across the motor now up and down and have the same torque working. Plus I have the ability here to adjust the sensitivity of the torque as well. Now I'll show you how this circuit works. Here we go. We have the positive supply here. That can be variable. That feeds down through Q1, which is a parallel transistor, through a series resistance here, and that's needed to put a voltage drop across there that's going to be used to feed back current back to this transistor here. The current flowing through Q1 goes to the motor to ground. It's self-biased with a voltage divider to its base, this resistor and this resistor here. And then we have an extra transistor here that goes across this resistor, which will act as a variable resistor that will come on when it's necessary. And we have an opto isolator here. And then we have the feedback transistor. So what happens is, under normal running conditions, I have this designed that this here voltage at the base will be about the same voltage as it is at the motor here. Okay, so the Q2 is at cutoff right now. No matter how much I raise the voltage on and lower the voltage on the supply, the base here will track the motor voltage and keep that 0.7 volts difference. We'll keep that voltage difference there as it needs to be. Now, the way it happens is, under normal running conditions, this transistor is at cutoff, and so everything connected to its collector is at cutoff. The opto isolator is off, and the motor is running through Q1. As I put a load on the motor, some of that current now builds up a voltage across this resistor here. A negative signal now is being applied to the emitter of the Q2, causing that some of that signal current now to flow through Q2. That flows through the opto isolator, through the indicator, through the opto isolator, which then puts a little voltage there onto the base of this transistor that it feeds into, which then causes the base of Q3 to raise in value, which then puts its emitter at a higher voltage to the base of Q2, causing Q2 to turn on harder to source more current to the motor now. And then as this here motor goes to complete stall, then you got maximum current flowing through here, because all that current now flowing through here causes this to go to almost saturation, and this here is almost saturation. It depends on the collector voltage and things like that, but where it can't draw any more current from the base, and this transistor now is feeding full current to the motor. That's why this here torque converter works really nice for variable supply voltages, because it's all running now off the supply. The base voltage here and the emitter voltage and the motor voltage is all run off the supply directly now, while with the other ones here they were running separate. That's why I'm able to have this here track properly now for different supply voltage values. So that's my version of my torque converter, and I can just scale this up now with power resistors and power transistors to work on my project for my mini lathe motor control speed controller now, as I've been working on this to do now. Okay, so that's the update here on my torque control design for this circuit. And okay, thanks for watching. Bye.